From the front side, the mountain is a sheer cliff that could never be scaled in one giant leap. For Dawkins, this represents the impossibility of creating a complex animal by chance alone. Yet Dawkins also envisioned an alternative route up the backside of Mount Improbable, a long, gradually sloping trail of small steps leading all the way to the summit.
According to Dawkins, that's how you'd climb the mountain. And that's also how you'd build a Cambrian animal, one small step at a time. What chance alone can't accomplish in one blind leap, natural selection can accomplish through the cumulative effect of many small incremental steps.
In theory, each step corresponds to a small unit of biological change, a new gene and its protein product. But do mutations and natural selection have a reasonable chance of producing even one protein in the time available? Since 1992, molecular biologist Doug Axe has examined this question.
There's a story that's being told, and there's a appeal in the case of Darwinism to random mutation and natural selection as being, in vague terms, the mechanism. But if you look at the detail, what kind of mutation can accomplish these transitions? And there, it's important to realize that the one area where we can really nail this down is at the single protein level, where you can actually measure it. And if you look at protein structures, to get a substantially new protein fold is prohibitively difficult.
Each of the thousands of different proteins in nature is actually a chain made from a specific combination of 20 different amino acids. The sequential order of these chemical building blocks is crucial, for if they are arranged correctly, the chain folds into a functioning three-dimensional molecule. But if the amino acids are incorrectly assembled, no protein will form. If proteins are indeed rare among the possible sequences of amino acids, what are the odds that mutations would stumble upon a functional combination of chemicals from the vast number of alternatives? To find out, Axe randomly altered the structure of an enzyme protein comprised of 150 amino acids.
You've got the protein 150 amino acids long, then you've got 20 to the 150th power possible ways of arranging the amino acids. Out of all those possibilities, how many are functional and how many are gibberish?
If you do the experiments and you analyze how much information is required to get, say, a new protein fold, it's just far beyond what you can get by random mutation and natural selection.
How far beyond? Axe published his findings in the Journal of Molecular Biology. He determined that among all the possible amino acid combinations, the probability of generating just one short protein by mutation is roughly 1 in 10 to the 74th power, or 1 chance in 100 trillion, 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 trillion.
To put that in context, there's only 10 to the 65 atoms in the entire galaxy. So to build a new functional protein by selection and mutation within the time allowed for the Cambrian explosion, what you're essentially having to do is equivalent to a blindfolded man looking throughout the entire galaxy for one marked atom. So what we're talking about is searching for a tiny, tiny needle in an enormous haystack and having a very limited time to search.
So on the question of something like the Cambrian explosion, there does not appear to be any way that unguided random mutations can accomplish what needs to be accomplished to explain new functional proteins. And certainly by extension, wherever in the history of life you would need to have multiple new protein folds, the probabilities multiply. So there's no reason to think that this is plausible.
Let me ask you a question.
Yeah.
Darwin wrote The Origin of Species in 1859, published it in 1859. He had an idea of the cell as being quite simple, correct?
Yeah, everybody did.
Okay. If he thought of the cell as being a Buick, what is the cell now in terms of its complexity by comparison?
A galaxy.
If Darwin thought a cell was, say, a mud hut, what do we now know that a cell is?
More complicated than a Saturn V.
So what is in a cell as far as we know now?
A world that Darwin never could have imagined.
I needed someone who could give me a glimpse into this world. So we went to molecular biologist Doug Axe.
Think of a cell as being a nanofactory, a factory where, on a very small scale, digital instructions are being used to make the components of the factory. Here we have the famous DNA double helix. You can see the two helical strands that are intertwined and wind around each other on the outside of the molecule. This is the material that stores all of our genetic information. In higher life forms, this will be the equivalent of something like a gigabyte of information stored in the molecules that form the individual chromosomes, all packed within the nucleus, which is a tiny fraction of the entire cell size. So what does DNA do? Well, the information in DNA ends up providing the information for sequencing the amino acids to make protein. So we have information in a one-dimensional form that provides the information for a three-dimensional form.
I'm finally just beginning to grasp the complexity of the cell. Are there systems within the cell that go well beyond Darwinian evolution? Some type of cellular technology that drives adaptation, replication, quality control, and repair? What if these new mechanisms have massive design implications? Well, I say, so be it.
The cell really is like nothing we've ever seen in the physical world. That's got to be firmly grasped. That's not something we can just say, oh, well, it's just a little bit more of the same old, same old. It's not the same old, same old.
We are finding is that there's information that's in the cell that cannot be accounted for in terms of these undirected material causes. So
It has to be.
and so there's some other, so there has to be an information source.
So one of the key questions faced by modern biology is, where do you get information from?